Here are solutions to homework set number 4 for ECE 111 Intro to ECE. In this week's homework, we're looking at using Matlab to solve problems that you'll encounter when you take Math 129, linear algebra. Now, linear algebra is all about solving n equations and unknowns. That is a common problem that you run into in electrical computer engineering. You're going to be using this trick over and over again. And essentially, the main trick that we use in the program is if I can take a problem and reduce it to solving n equations and unknowns, then I can solve it with Matlab. The challenge is setting up the n equations and unknowns. Well, this week's homework is, assuming you did that, how do you solve? To do that, that uses a thing called matrices. In Matlab is a matrix language. So to input a matrix in Matlab, where's Matlab? So do this, let's say A equals square bracket start a matrix, 1, 2, 3, semicolon is next row, 4, 5, 6. I've got a matrix. If I have a second matrix, B equals 1, 7, 4, next row, 6, 4, 2, I can now add them. C is A plus B. I can transpose matrix. That's a single quote. That's A transpose. I can do what is A transpose times A. I can find a matrix inverse. And this one's just not going to like. Let's try A times A transpose. And find the inverse of A times A transpose. So matrices are really easy to work with in Matlab. That's really one of the main features of Matlab. It's not just a graphing calculator, it's a graphing calculator that does matrices. So, going back to the homework, suppose I want to solve two equations, two unknowns. The first trick is to put it in matrix form. So what I would do is pick the order. I'm going to choose X and Y. You could switch the order. As long as you're consistent, it works either way. With a matrix, when I multiply two matrices, the first element is times the first element, so this first column is times X, the second one is times Y. The first equation is 4X minus 4Y is 3. The second equation, 5X minus plus 4Y is minus 7. So doing that, here's the matrix form. I'll represent that with variables. This is B, this is X, this is A. X is then the inverse of B times A. In Matlab, I would input that. B is the start of the matrix, 4 minus 4, next row, 5, 4. A is 3, next row, minus 7. Then X is the inverse of B times A. There's your answer. Two equations, two unknowns. If I have three equations, three unknowns, same procedure. I would put this in matrix form. Let's call that X, Y, Z. So first column is times X, second column is times Y, third column times Z. First equation is 8X plus 3Y minus 5Z is 4. Second equation, third equation. Same procedure. In Matlab, I input the B matrix. That's 8. And I got a typo here. That should be a 3. 3 minus 5, 0, 2 minus 5, 9 minus 6, 0. Your A matrix, and the wrong answer, because I typed the matrix in wrong, would be here. 4 equations, 4 unknowns. So basically, as long as I can set it up as n equations, n unknowns, I don't really care. 2 equations, 2 unknowns, 3 equations, 3 unknowns, 4 equations, 4 unknowns. Matlab can solve. What's important is get the equations right. And it's also important that you type it in correctly. So that's the first three problems. The next set of problems is suppose I have more equations than unknowns. In that case, what you do is I have y is my basis function times x. Oops, I guess I'll call that a. Yeah, y, whatever. If I have more equations than unknowns, like if I have 3 sets of equations and 2 unknowns, so this would be like your AB, I cannot invert a 3 by 2 matrix. So the trick is multiplying the left by B transpose. When I do that, this is a 2 by 3 matrix. 2 by 3 times 3 by 2 is a square matrix. I can invert that. So multiplying the left by B transpose B inverse, this cancels, and I get the answer. So this is the least squares solution. B transpose B inverse times B transpose times Y are my unknowns. What that does is if you have a bunch of data points, like so, it's going to find out what curve minimizes the sum square difference. Hence the name least squares. And rather than just give you random data, let's look at some real data. If you go to National Oceanic Atmospheric Administration, they've been recording CO2 levels since 1958. Here's what it looks like. Is there a trend? Let's do a curve fit. So problem 4 is do a parabolic curve fit. The trick there is I'm going to express this as y is b times a. This is my basis function. To do a parabolic curve fit, I want the basis to be year squared, year, and 1. Here's my unknowns, and here's y. So go to Bison Academy, or go to NOAA, pull in the data. Let's see. So here's what it looks like. I'll do data equals square bracket starting matrix, copy paste, end of matrix. I didn't throw in all the data there. There's a whole bunch. Pull off the third column, that's the year. Pull off the fourth column, that's the CO2 levels. Now set up the basis function, year squared, year, and 1. And then here's your least squares curve fit. We're going to be doing that over and over again in this homework set. When I do that, I get 3 numbers. That's the weighting on year squared, year, and 1. To check my answer, I'll plot it. Plot year versus CO2, year versus curve fit, and that's what it looks like. The blue line is the data, the red line is my curve fit. Matches pretty well. Once I get the data, I can start asking questions. Like, when is the CO2 level going to reach 400 parts per million? Well, I can just sit there and go over here and look at it. I can also do that in Matlab. That's the roots command. Roots finds when a function equals 0. To do function equals 400, I'll just shift it by 400. So this is year squared, year, and 1. And year 2014, right here, go draw the line straight, is when it'll be 400 parts per million. I can start predicting the future. When do we reach 600 parts per million? That'll be year 2079. When do we reach 2,000 parts per million? 2286. Again, this is kind of stretching it, but this says if nothing else changes, based upon the current trend, that's when we can expect to reach 600 and 2,000 parts per million. If you grab a second data set, this is the temperature of Fargo. The first column is the year, 14th column is the average temperature for the year. If I pull in the data, that'd be, go to Bison Academy, 111, right here, Fargo temperature, there's your data. Pull in the data, pull out the first column, pull out the 14th column, and then plot it. That's the blue line, that's what it looks like. To come up with a linear curve fit, the red line, I would say my basis is year and 1. My least squares curve fit, inverse of B transpose B, B transpose times temperature, I get 2 numbers. There's the slope, the number times year, and the constant. Plot the 2 together, and yeah, it looks like a pretty good curve fit. With that, I can answer questions like, how much has Fargo warmed up over the last 80 years? Here's the slope, the first element, the slope times 80 years. Fargo's gotten about 3.4 degrees warmer over the last 80 years. What does that mean? I don't really know. It could just mean that Fargo's grown. Cities are warmer than the countryside. Could mean that Fargo's grown over the last 80 years. It has. Could mean that the climate's changing. I don't really know. I can predict. What will the temperature be in 2050? it'll be 44 degrees, 2100, 46 degrees. So Fargo's definitely getting warmer. If the trend continues, we can expect us to be 2 to 4 degrees warmer by then. Let's take another data set. Again, just kind of for fun. Once I can curve it, I can curve it anything. Let's curve it the Arctic sea ice level. Again, go to the National Snow and Ice Data Center or Bison Academy. I can pull in the data. When I do that, the first column, let's do that. Going over here, this is the sea ice level. First column is the minimum, second column is the maximum. If I plot the minimum versus year, that's the blue line. If I want to do a linear curve it, my basis is year and 1, least squares, slope, offset. I get the red line. Once I get the curve fit, I can say, when is the Arctic going to be ice-free? That should be in the year 2074. First time in 5 million years. We're going to live to see that. Oh, you might live to see that. I may or may not. Problem 7. Let's do a parabolic curve fit. A linear curve fit assumes the ice is melting at a constant rate. A parabolic curve fit says that the rate of melt is increasing year by year. That's probably actually more realistic, because as ice melts, it exposes more water, which absorbs more sunlight, causing more ice to melt. A parabolic curve fit, all you do is change the basis to year squared, year, and 1. I get my 3 constants, year squared, year, and 1. Plot the two together, I get maybe a slightly better curve fit. Using parabolic curve fit, I should be ice-free in the year 2057. 32 years from now. World temperatures. NASA Goddard's been recording temperatures since 1880. Let's just look at the years 1880 to 1920. If I just grab that set of data, let's go back to Bison Academy. If I do temperature deviations, grab the data from 1880 to 1990. Here's what the data looks like. Let's do a linear curve fit. So paste the data, here's my basis, least squares curve fit. It actually looked like the Earth was cooling off. That was one of the concerns we had back at the turn of the century, well, the previous turn of the century, 1900. It was feared that we were entering another ice age. Assuming that trend continued, by this year, we should be minus 0.7 degrees. Let's look at all the data. All the data looks like the blue line. Let's do a parabolic curve fit. Again, to do that, the basis is year squared, year, and 1. The 3 numbers, plot the two together. That's a pretty reasonable curve fit. Kind of misses the last couple points. Last 2 years, the hottest on record. From that, I can say, what will the temperature be in the year 2100? So just do A times year squared plus B times year plus C, which should be 3 degrees above average. So the Paris Climate Accord tried to keep us 1.5 degrees above average. Current trend says we're going to be about 3 degrees above average. I can find out when we'll be 10 degrees above average. That's about the year 2251, 225 years from now. The last problem, what does that mean? Well, this actually isn't graded. It gets too political. But been some studies on that, and here's kind of what it means. The study comes out of the Netherlands, so it's kind of more focused on Europe, but kind of get the same idea for the US. At 1 degree, summers are like 2003, which caused 10,000 deaths in France. The flows of rivers decrease, crop production suffers. That already happened. 2 degrees, that'll be in about the year 2067. Oceans absorb less CO2, just the oceans are too hot. Soils start to release CO2. Vacations to the Mediterranean or Gulf of Mexico are just too hot. Start getting crop failures in Central and South America, causing mass migrations. We can expect that in about the year 2067, assuming nothing changes. At 3 degrees, turn of the century, you're getting crop failures in China, billions of people on the move, collapse of equatorial governments, something we have to look forward to. 4 degrees. Spain, Mexico become deserts, mass migration to northern latitudes, rainforests dry up. At 6 degrees, ice caps are gone, methane hydrates become unstable, in a positive feedback loop, ocean circulation stops, hydrogen sulfide gas sterilizes the atmosphere, ozone layer depletes. Basically really, really bad. That's about the year 2175. Is that scary? You betcha. That's kind of why we're trying to get away from fossil fuels. They're basically killing the planet. But all is not lost. That is part of the reason we have the next lecture. There are ways around this. There are ways to produce energy without using fossil fuels. That's solar, wind, that's us. That's electrical engineers. So if you go on to the next lecture, lecture number 5, this looks at renewable energy. One of the reasons for pushing towards renewable energy, well, one of them, they're cheaper than fossil fuels, but also this right here, we can see a cliff coming up. It'd be kind of nice to avoid that cliff. But that is homework set number 4. The thing to note about this for this class is Matlab is a really, really powerful tool. With Matlab, I can solve n equations and unknowns. With Matlab, I can curve it. And I can curve it just about anything. I can curve it made-up data. I can curve it real data. As an engineer, once you have Matlab, you can analyze data yourself. That's homework set number 4 for ECE 111.